So we're talking about limitations, right? And then we are saying that there can be skeletal rearrangement of the alkyl electrophile into a more stable carbocation, either through 1,2 hydride shift or 1,2 alkyl shift. So always after the lowest acid has done its work of forming the carbocation, right? The next thing is that the compound will ask itself, can I move just one atom to produce a more stable carbocation? If that is possible, then it will move. So usually sometimes the intended substituent will change a little bit. It will change because the compound itself will rearrange to form a more stable form of itself and present you a product. Right? Does it make sense? Good. So that is the whole thing. And then the next thing that we have to note about this is that usually if the arrangement is from primary to secondary, you have a mixture of products forming. So assuming I was primary and I have rearranged to form secondary, means you get two products, primary and then secondary. The secondary will be the major product and the primary will be the minor product. If it was secondary and it was moving to tertiary, right? What will happen is that you would have a mixture of products. So you have secondary, tertiary, and then the tertiary will be the major product. Very simple. But then assuming it is moving from primary to tertiary, if it's moving from primary to tertiary, then you have one product. The primary will not form at all. It is only the tertiary that will form. It is only the tertiary that will form. So you have to take note of this. That if the jump is, let's say we have a primary carbocation and we have to do a rearrangement to form a tertiary, it is only the tertiary that will form. Good. So let's look at this example. Very simple. Good. So we have this compound. If I'm supposed to open up the structure, it's CH3, CH2, 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 Cl. If this is taken away, we would have the plus forming here, right? The plus forming here is primary. Good. Now I realize the product, the one that still has the primary, is the 35% of the product. 65% is something else, and that is because of the hydra shift. That is after a positive charge has been formed on this carbon, which is primary. This hydrogen would move. It moves as a hydride. That's what we call the hydride. So it moves as H minus. So it moves with all the electrons here. That's why we are moving it from the electrons. It moves and then it comes here. When it comes here, there's no more positive charge here, but then the positive charge will be deposited here. And this is a secondary carbocation, which is more stable. So because of this rearrangement, you'd form a more stable carbocation, and then that will be the major product. So from primary to secondary, two products. Does that make sense? The next one, we don't have a hydrogen, we have an alkyl shift, right? So what happened here is that this is the compound. It's like this, okay. So CH3, 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 CH2, Cl. So this is it. Now, if I move the Cl from here, the positive charge will be deposited here. It will be here. Right, good. Now, this is primary. But then if you move one alkyl group from here to here, what you get is that the positive charge will be here, and that will be tertiary. So after producing your primary, the compound will realize that if I am able to shift this alkyl group, I'll get tertiary. So what will happen is that this alkyl group will be shifted, will be moved. Now, it is moving with the electrons, so it moves onto this carbon, right? Good. So that it can continue this carbon, and the positive charge will be where it was initially. And this is tertiary. Because it's moving from primary to tertiary, only one product will form. Only one product. That's only the tertiary product will form. And that's a limitation. Because I assume you wanted to put this on the benzene ring, and what you are getting is totally different. So that's a limitation. And this is what we call the rearrangement to form a more stable one. Alkyl or hydride shift. Very simple. Very simple. Yes, so let's move on. Good. Note, aromatic alkylation reaction occurs in a number of biosynthetic pathways, such as synthesis of vitamin K1. So always sometimes you question yourself that why am I learning all these things? But then when some of these things come in, you become a little bit at ease because you know what you are doing is something which is real, something which is really happening, then you are learning it very simple. So they are saying that alkylation is in formation of vitamin K1. Very simple. Now, the next synthesis, I've already mentioned it, that is Friedel-Crafts acylation. Acylation. So acylation, what you need is an acyl chloride. So you need your benzene ring, the acyl chloride, and then an obvious catalyst, AlCl3, right? Good. Now, what will happen? Very simple. Always the lowest acid will create a positive charge from this, right? And then the benzene ring will attack it. So that's what we have. So it's like we cut this one off and everything joins to one benzene ring here, right? Good. Now, we are saying that, okay, so they are showing how the lowest acid will form an electrophile out of the acyl group. So that's what will happen here. If I'm supposed to show the actual mechanism, which I've shown a lot of time, the alone pairs here which can be deposited on or donated to the Al. When the new bond forms here between the aluminium and the chlorine, it will be positively charged, right? Good. Now the bond here will break onto the chlorine to neutralize the positive charge, right? Neutralize the positive charge, and then breaking this bond will form a positive charge on this carbon, and that is what's happening here. Now, when this happens, this electrophile is stabilized by resonance. Now, because it is stabilized by resonance, there is no rearrangement. There's no skeletal rearrangement to form a more stable carbocation. That thing does not exist again because the intermediate here is what is stabilized by resonance. The next thing that happens here is that polyalkylation is also solved. There were more problems that we talked about in alkylation, but two of them is being solved here. We don't have any skeletal rearrangements. The next thing is that we don't have any polyalkylation occurring. That is because the intermediate electrophile formed here is stabilized by resonance. Very simple, right? So we can keep this reaction in our head. It makes sense. I mean, we have always been saying that the lowest acid will try and form an electrophile. And then we are saying in this case, the electrophile is being stabilized. Let's talk about the stabilization a little bit before we move on. So stabilization is like this: electrons here on this oxygen being donated here. Right? Once you donate it, will form triple bond, and then because oxygen has donated this electron, it will have positive charge here, right? And then it can go back. That is, this bond can break back onto the oxygen. When it breaks back like that, we'll have the positive charge on the carbon as here, and then the positive charge will move away from the oxygen. Very simple. Very simple. Good. So we are saying notes. There's no polyacylation. Very simple. And we have talked about that. There's a question for us to try our hands on. The question says benzene reacts with 2-chloro-3-methyl butane in the presence of a catalyst, obvious catalyst. I mean, how many products are expected? Then we are saying that what are the structures of the expected product? Now we are saying that if more than one product is expected, explain how the major product is formed. So for this question, because we are expecting, we know, of course, we have benzene and then an alkene, right? An alkyl halide in the presence of AlCl3. So we are doing Friedel-Crafts alkylation. Anyways, Friedel-Crafts alkylation, we expect that sometimes there can be some skeletal rearrangement. So always, if you are not a pro, it is better for you to do the mechanism, for you to know where it is going to before you come and write the reaction, right? But then the pros, when they look at it, they can just know that there will be rearrangement. So let's try this question on a white sheet. Let's try this question on a white sheet. What we need, let me write the compound down: 2-chloro-3-methyl butane. So the first thing we have to do is to draw the structure of 2-chloro-3-methyl butane. Very important, right? 2-chloro-3-methyl butane. So 2-chloro. So butane, I mean, we always start from the parent name. 1, 2, 3, 4, butane, right? Now 2-chloro. On the second carbon, there's chloro. On the third carbon, there's methyl, right? And I can make CH3, CH, CH, CH3. So this is the compound, right? Good. Now, yes. If I remove, so I'm trying to work around it. I mean, to know the possible product. Now, this carbon here, if I remove the chlorine here, the positive charge will be here, deposited on the carbon. So the positive charge will be here. Right, good. Now, this is a secondary. I am asking myself, can I shift anything so that I can get tertiary? Ideally, if you are supposed to move this hydrogen to this side, right? If you are supposed to move this hydrogen here for the positive to be here, this carbon here is a tertiary carbocation, tertiary carbon. So the cation form here will be tertiary carbocation. Good. It means you can actually shift it. And so if before I do the mechanism, I can just know that you form two products. That is, if I am reacting this plus benzene, right? Good. I am getting something like this. The first product will be something like this. So it is my benzene plus the C. This is the C, right? So this C has CH3 here. It has H attached to it. It has CH. It has CH3. Then it has CH3. So that's the obvious product. The next one is when I move my hydrogen here, right? When I move my hydrogen here to put my carbocation here. Good. And so in that instance, I would have this product. So this carbon is the focus now, right? On top of it, I would have CH2, CH3. Now CH2, because this hydrogen will move here, so we make this one CH2. This hydrogen is moving here, right? Go to CH2, CH3. And then it has CH3, it has CH3. So I'm expecting more than one product. Yes, because I can form a tertiary. Now, these are the two products I'm expecting. Then it's saying that if that is so, I should show the major product. This is the major product because it's coming out of the most stable carbocation, right? So this is the major product. And then the last thing I'm supposed to do is that show the mechanism by which the major product was formed. So let me do that on the same page. And let me clean some of the space here and then show the major product. So the major product. Okay. So, okay, I have to draw the compound again. Right. So this is the compound C, chlorine here. Oh, sorry. So chlorine here, CH3 here. Right. So CH3, H, CH3. Very simple. Now, the first thing that will happen is I show the mechanism. So plus AlCl3. Then we'll remove this. So I'll have AlCl4 minus plus I'll have CH3, CH, CH3, CH3. So plus here, right? So plus there. Now you realize that the only difference that I've removed this chlorine, so this chlorine moves away, and then the plus is deposited here. Now, of course, I can do skeletal rearrangement, right? So what will happen here is I have to do my hydride shift. Now, let me draw this compound again. I'm drawing the same compound again. So CH3, CH, CH3, CH3. Class is here. Good. So I have to show my hydride shift. Now I know if I move this hydrogen, right? If I move this hydrogen, so I'm moving. If I move this hydrogen to the side, right? What I'll get. So what I'll get. So this is my hydride shift. Oh, this is my hydride shift. So if I move this, the positive charge will be deposited here. So that is what I'm showing now. Now, this hydrogen is not coming from anywhere. It's this same hydrogen. I decided because I'm showing a movement, right? That is why I decided to remove it like that. CH3, CH2. Now it's now CH2 because a new hydrogen has been added, right? Then the next C will be CH3 plus, because it has lost the hydride. So this is the tertiary carbocation. Good. Now from here, from supposed to the mechanism, very simple. So it will be the benzene ring coming in with its pi. Sorry, let me clean this one. My benzene ring is not benzene. So it will come in with its pi electrons, will come and attack this carbon. So I would have my first, it's just 2 steps, right? I have my first intermediate. So here, it can be here, and then here. So hydrogen here. Then I'll have the CH3. Then I'll have CH2, CH3. Very simple. Good. And then there'll be a plus here. Then the base in this medium was AlCl4 minus, right? We'll come and take this hydrogen, right? And the bond will break onto this. So I would have my final product. So something like this. CH2, CH3, 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 plus some side product if you want to show AlCl3 plus HCl. Very simple. Very simple. So that would be that for that question. That's all for that question. And remember, if we are forming primary and secondary 2 product, that's it moves from primary, secondary 2 product. If it's primary to tertiary, it is just 1 product. If it's secondary to tertiary, 2 products. 2 products. Okay, so let's go back to our slides and finish up. Good. Clemenson's reduction. So the last way of forming aromatic hydrocarbons. So in Clemenson, our starting material is as shown here, right? So we have this is like a ketone, right? This is a ketone. So we are not talking about only ketones, we are talking about carbonyls, right? Good. But then the specific one shown in this example, this one here is a ketone. Good. Now what are we doing? We are just reducing it. Reducing it is like removing the oxygen. So reduction. Oxidation is addition of oxygen, reduction can be loss of oxygen. So removing the oxygen here. So the next thing that we will do here is that we will remove this oxygen. And then we add hydrogen. So we remove oxygen, and the 2 bonds here will be connected differently to hydrogen. So very simple. The ET here is ethyl. So that is this group. So the ethyl has not changed. It's the same ethyl here, right? Good. What has changed is this one. It was double bond O, and then we have removed the O, and then we have put 2 hydrogen in there. Very simple. So reduction, removing the oxygen. Very, very simple. Now, Wurth-Fitting's reaction. That's the last way of forming aromatic hydrocarbons as we've been taught. Now, in this reaction, we need an aryl halide, and then we also need an alkyl halide. So an alkyl halide, an aryl halide, and then we need dry sodium in dry ether. So sodium in dry ether. Now, this is how the mechanism will proceed. So the bromine will be moved away by the sodium. This one will also be removed by the sodium. They are good living groups anyways, right? Good. And then there will be direct connection between what I'm talking about is not the mechanism anyways. So there's direct connection between the carbon that was bonded to the Br and then the ring where the Br was, right? So direct connection. Very simple. And then we'll form a byproduct like this. Very simple, right? There are not a lot of explanation because he will not stress us when it comes to this. So he can just have our head up. Now, we are saying that in alkyl benzenes, alkyl substituents react as aliphatics, while the phenyl substituent reacts as aromatics. So for this one, right, if you have an alkyl group like this one reacts or react as aliphatic, and then this part will react as aromatic. So that's what they are saying, right? Now we are saying that we can oxidize the alkyl group. So if you have a very strong oxidizing agent like KMNO4, KMNO4 is a very strong oxidizing agent. It can convert this to what? To benzoic acid. So sometimes we can ask you to synthesize benzoic acid. What you have to do is that you have to put an alkyl group. So you can put an alkyl group on the benzene ring. After putting an alkyl group, you can use Friedel-Crafts or any other thing to put an alkyl group on the benzene ring. After putting the alkyl group, you can oxidize the irrespective of the length of the chain. You want to say, sorry, assuming there's like 10 carbons, I use a different language. Assuming there are 10 carbons on the chain and you still put KMNO4, it would form benzoic acid. Irrespective of the chain length, you get benzoic acid, right? That is what we are talking about with respect to this. So that's here. So always you form benzoic acid if you oxidize it strongly, the strong oxidizing agent, right? Good. So that's now we have some questions to try our hands on. The first one, we are saying that we have this starting material. So benzene as a starting material, we should form benzamide and acetanilide. So the first one, we would solve them on white sheets. Let's get white sheet for benzamide. So benzamide. So we have benzene, right? We want to take it to our benzamide. Huh? Okay. Oh no, I'm forgetting my compound. So we are taking it to benzamide, CONH2. Right. This is it. We are taking it to benzamide. Good. Now, the basic steps are the same. We have to go and form benzoic acid. From the benzoic acid perspective, then the narration changes a little bit. But we'll talk about the two different scenarios, right? The narration changes a little, but we'll talk about it. So how do we form our benzoic acid? I'd like to use Friedel-Crafts. We can do alkylation through so many means, right? But I'm using Friedel-Crafts. So this plus, let's say CH3Cl plus AlCl3. I can do this. Some people want to put the AlCl3 because the catalyst, you'd want to put it on the arrow sign. It's fine. So this, it's always better for you to put the catalyst here. Okay, so this. Now we'll get so we have this. That is the first step, right? There are other side products, but we are not interested in that. So we just focus on this one. Then what we have to get KMNO4. KMNO4. Usually KMNO4 in acidic medium is very high. That's the strength of oxidation is very high. So sometimes we use alkaline medium to reduce the strength a little bit, right? Good. So from here we'll have our benzoic acid. COOH. As I said, it's uniform up to this stage. From here, we change the narration a little bit. Good. Now, for you to form your alkyl halide, you can use so many means and so many alkyl groups, right? So many means. Good. So I use the Friedel-Crafts. You can use Woods fitting. You can use Clemenson's reduction. Each of them will be fine, right? Good. Good. But make sure benzene is a starting material too. Now, from here, two ways. So some people will decide to add ammonia straight up. But if you add ammonia and you want a good yield, you have to add heat. So ammonia and heat. And this can give you the benzamine that you want. No two ways about that, right? So you can get the benzamine that you want. Good. That is it. The next way is if you don't want to add your ammonia heat, you can change this to an acyl chloride. So we have benzoyl chloride. Now, benzoyl, this is the benzoyl functional group. Benzoyl functional group. So CO. So benzene ring plus CO. That's C double one O is benzoyl. Right. So we are changing it to benzoyl chloride. So okay, functional groups. Good. The benzoic acid, COOH. Now we can add PCl5. That's one reagent. If you don't want to use it, you can use SOCl2. Now don't use both of them, use one of them, right? This will give you your benzoyl chloride, very reactive reagent. So from here we can add our ammonia. From here we can add our ammonia. When we add ammonia, we'll get our benzamide. Very simple. We'll get our benzamide. So very simple. Very simple. Good. Good. So that is that for the first question. The second question, what are we supposed to draw? Acetanilide. Good. So let's go to our acetanilide. 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 So acetanilide, let me change the ink. Red. So this is benzene. We want to take it to acetanilide, right? Mm, You have to always draw your final product so that you know where you are going to. I mean, very important. So this is acetanilide, right? Good. Now, yes. So from here, you realize that you have to obviously add aniline, right? Sorry, not aniline. Amino functional group here. Once you add the amino functional group, then you can try and add your acyl group. So always that's what will show you what you are supposed to do. You can just look at the compound and know the pathway, right? If I look at this compound, I mean, there's NH here. So it means I have to add NH2 to the compound. And then before I add my acyl group. Now, how would I add my NH2? I have to first add NO, nitration. So I have my benzene ring here. For me to nitrate, I need these two reagents. I need nitric acid, concentrated one in A2SO4. We just talked about this. Then this one will help me get my nitrobenzene. After getting my nitrobenzene, I can reduce it in the presence of excess hydrogen and then platinum palladium catalyst. Sorry. So I'm getting. You can also use platinum anyways. And it's 2, right? Good. Now after getting this one, there are 2 arguable ways of going about it, but the most preferable way is use your acetic anhydride. You don't use acetic acid, even though acetic acid can also do it arguably, but then use acetic anhydride. So this is how we do acetic anhydride. So this is it, right? Among so many other ways of drawing it. Some people write it CH3CO 2O. So this is also acetic anhydride, right? So use your acetic anhydride to introduce your acyl group. So we have so that is it. This is very simple. So you have your acetanilide. Arguably, people can also use instead of the acetic anhydride, acetic acid, but the best is to use your acetic anhydride. Very simple. Very simple. Good. Let's go back to the slide and then continue. Good. So these questions done. Next slide. Now, effect of substituent in electrophilic aromatic reaction. So this is a whole new different discussion and we'll talk about it in the next video, right? If you have any questions, as I always see any member of the GPAC academic board for further clarification. Thank you very much.